Hello everyone, welcome back. So today we are looking at entropy and we are in our decision tree series. So we're looking at entropy. What is entropy? Entropy is a measure of uncertainty or disorder in data, okay? Uncertainty or disorder in data. So I want you to imagine a box of fruits with let's say apples and oranges, okay? Apples and oranges, okay? I feel like this is our favorite example in the channel, although no, we have a few favorites, but okay, there is a box of apples and oranges. So this box is mixed, right? It has a mix of apples and oranges and it is messy and it's uncertain. Messy and uncertain because when you try to go pick something, it could be an apple or it could be an orange. So it's harder to predict what fruit you will pick next. So when this happens, when it's harder to know what you might pick next, we essentially say that there is higher entropy. Because what is entropy? Entropy is uncertainty or disorder in your data. But let's say your box is pure. Your box is pure. This one just has oranges and this one just has apple. Now you have better certainty, right? When you go dig in this box, you know it's always going to be orange, and here, like, you always know it's going to be an apple. So if the box only has apples like this or only oranges, then it's very organized, right? So there is no confusion. Organized, there's no confusion. So entropy is low entropy, okay? Low entropy. So what is entropy? Entropy is uncertainty or disorder in your data, something like this, where there's a lot of mix happening, then that's messy and uncertain, so it has higher entropy. Whereas something like this, where it's like perfectly in its own basket and it's very organized, and whenever you go to pick the fruit, you know, you can sort of predict what fruit you will pick next, then that has lower entropy, okay? So I hope that makes sense. And I want us to look at an example and also look at the math a little bit. So we're gonna actually get our calculators out and look at the formula and try a little bit of math, and get a feel of how entropy helps us to decide the best way to split our data when building a decision tree. So the formula for entropy, and I've realized I don't write formulas very neatly, so I'm going to take some time when I write the formulas so that it's easy for you to copy it down. So formula for entropy looks something like this. And if you want, let me know, we can derive it. Right now we're just going to walk through the formula, but if you want to know the origin of it, we can do the derivation as well. So the formula looks like this, but for our binary classification problems like yes or no or pass or fail, we simplify the formula to be this: P1 log 2 P1 minus P2 log 2 P2, okay? Then this is what I want you to remember for our classification problem. Classification problems, okay? So before I forget, P1 is simply probability of one class. So if we're looking at our pass-fail example, then the probability of it belonging to the pass class. So this one's just probability of one class in our binary classification problems, and then this is probability of the other class. If we look at whether a student might pass or fail classification problem, this could be pass and then this could be fail, okay? So this is one and then this is the other. So this formula, whatever we gain from this, tells us how mixed our data is. And let's walk through one example. We talked about pass or fail, so why not just build on that? So let's say I have 10 students, and then I have data on whether they passed or failed. Okay, 1 2 3 4 5 6 7 8 9 10, and then for the sake of simplicity, I'm just going to say the first 5 passed, and then the rest failed. Okay, so 5 passed, 5 failed. So when we look at this, what is our probability? For our p-pass, it will look like this, right? So our p-pass here would be 5 out of 10, right? 5 out of 10, right? So that would be 0.5. And then what would it be for our fail? Let's say p fail then is also 5 out of 10, or 0.5. 5 out of the whole 10, right? So let's calculate the entropy using our formula for a binary classification problem. Okay, so our entropy then is, let me calculate with this, would just be negative 0.5 log to 0.5, and then plus 0.5 log to 0.5, and I'm taking negative common because you see both of these have negative values, so I'm just taking negative common. So when I calculate it, this log to 0.5 is negative 1, so that would be, where did it go? Okay, 0.5 times negative 1 plus 0.5 times negative 1. So that would just be negative 0.5, negative 0.5, or 1, negative 1, and that would simply be 1, right? So our entropy is 1 here. What does that mean? 1 means, if it's 1, it means data is perfectly mixed. Okay, sorry, I had to take a break. Okay, so entropy of 1 means that is perfectly mixed and there's maximum disorder. Okay, so this is what entropy 1 means. Now let's look at another example. Let's say here we had 5 pass and 5 fail, but now let's say my data is all pure. What does that mean? I either have all pass or all fail. For this example, we are considering everybody passed. So if everybody passed, then my p-pass will look like 10 out of 10 because everybody passed, right? And then my p-fail will look like 0 out of 10 because 0 failed the exam, so that would be 0. So what will my entropy be? Would just be 1 log to 1 plus 0 log to 0, right? So when I calculate that, log to 1 is 0, and then that would be 0 as well. So that just gives me, sorry, I'm just assuming this will be 0 because 0 times 0 is 0. So that would be negative 0, and that just is 0, right? So if entropy is 0, what does that mean? Data is completely pure. There's no disorder. That means for our decision tree, we don't need to split the data further because it's already pure. Okay, so here when we think about this, it's already pure, right? There's no more splitting that can be done. So think of this example when you're thinking of pure data, entropy 0. Okay, now let's look at another example. So let's say now p pass, my 7 out of 10 students passed, so that looks like 0.7. That means my fail is 3 out of 10, or 0.3. So what will my entropy be? My entropy then would be 0.7 log 2 0.7 plus 0.3 log 2 0.3. So that would be 0.7. From my notes, I think that's negative 515 plus 0.3 times, I think that is 1.737. I hope my calculation is correct. If not, I shouldn't be too off. And then that would just give me 0.360 negative 521. If you're following along, that should be okay. So what does this mean? This is greater than 0 but less than 1. It's somewhere in between, right? So this one, entropy is lower than 1, meaning that the data is less mixed than it was in this case, but it is more mixed than this case. So it's somewhere in between, okay? So I hope this helps you understand how to calculate entropy, and more importantly, how to interpret entropy with our examples. So let's circle back to why we need entropy in machine learning. So entropy in machine learning is important because one, it helps us, of course, build better decision trees. So we want to find best feature to split the data, right? For example, if we're looking at pass or fail, we want to find what the best feature is in order to split our data. So that could be our studied or did homework, whatever it could be, right? So what we do is we calculate entropy before splitting the data and then after splitting the data, okay? We calculate entropy before and after, and the feature that results in the largest entropy reduction is then chosen for the chosen as the best feature for the split, okay? So this brings us to our next idea. And sorry, one more thing. The goal here is to keep choosing features that make the groups less mixed. So that means lower entropy, purer data set, right? Better classification. So what are we trying to do here? Choose features that make the groups less mixed. That's all we're trying to do in our decision tree problems. So this brings us to our concept of information gain. How do we measure the effectiveness of a split? It's through information gain. Information gain is simply entropy before split minus entropy after split. This is your information gain, okay? So we choose the feature with the highest information gain because it provides the biggest reduction in uncertainty, okay? So choose feature with highest IG, okay? So in Crux, information gain is your numerical value that tells how well a split improves classification, okay? And this is how you calculate it. So I hope most of the concepts are clear. We can do a quick recap. So your entropy basically tells you how messy the data is, and then higher entropy means more mixed data, more uncertainty, and then your lower entropy means more pure data, right? So entropy helps us decide how to split the data in decision trees, and we split on the features that gives us the highest information gain. So these are the most fundamental concepts that you need to understand as we build our decision tree from scratch. If you want more in-depth derivation of the entropy formula, please let me know so that I can do a different video on this. But I really do want you to at least understand the intuition behind it, so that whenever we build it from scratch, you know what's happening and where everything's coming from. Okay, see you in the next video.